Well, we're going to continue talking about what we were talking about for the past couple of weeks. First, I want to mention that we just posted episode 13 of Ham College. Tommy and I shot that this past Friday. We talked about the history of SOS, and we also told you everything you needed to know about transistors to pass your technician exam. So go check that out if you're studying for your technician, hamcollege.tv. You know, I showed you one of these. We began, well, can you even see it? There we go. Yeah, thanks, Victor. We began talking about the Smith chart here 2 or 3 weeks ago, and I've been teasing you with it. And yes, I'm going to do it one more time, but after this episode, our smoking solder here, we're going to know what we need to do so that we can start using that Smith chart next month. Now, watch the segment here as we talk about VSWR this week, but at the end of it, you'll see a link on there where you can download a version of this Smith chart that I'm using here. And I'll encourage you to go download that and print it out for next week so you'll be ready to plot along at home. This week on Smoke and Solder, we're going to talk about VSWR. Every ham needs to understand SWR in order to maximize their transmission system. When a transmitter is connected to an antenna by a feed line, the impedance of the antenna and feed line must match exactly for maximum energy transfer from the feed line to the antenna to be possible. The impedance of the antenna varies based on many factors, including the antenna's natural resonance at the frequency being transmitted, the antenna's height above ground, and the size of the conductors used to build the antenna. When an antenna and feed line do not have matching impedances, some of the electrical energy cannot be transferred from the feed line to the antenna. Energy not transferred to the antenna is reflected back toward the transmitter. It's the interaction of these reflected waves with forward waves that causes standing wave patterns. Reflected power has three main implications in radio transmitters. The RF energy losses increase, there's distortion on the transmitter due to the reflected power from the load, and damage to the transmitter can occur. This animation shows two traveling waves. The blue wave is traveling to the right, and the red wave is traveling to the left. Here, both waves have the same amplitude, the same frequency, and the same wavelength. The black signal represents the energy of these two waves combined. As these waves pass through each other and add together, they create a standing wave. That's a pattern which neither moves left or right, but simply oscillates up and down as a function of time. The amplitude of this standing wave is twice that of the individual waves when the two waves are in phase, so that the peaks and valleys line up. The amplitude of the standing wave is zero when the two waves are completely opposite in phase, so that the peaks of one wave line up with the valleys of the other. The two waves' amplitude then cancel each other out. A great way to demonstrate standing waves is shown in the 1959 Bell Telephone Laboratories film with Dr. John Shive. Using a mechanical wave machine, Dr. Shive shows a visual representation of what standing waves look like.
This time you see the wave is reflected upside down. The reflection is still total as it was before, but the wave is inverted upon reflection.
I highly recommend you check out this film at the ATT archives. If we know the forward and reflected power of a circuit, we can calculate the SWR using the formula VSWR equals 1 plus the square root of reflected power divided by forward power over 1 minus the square root of reflected power divided by forward power. Let's solve the VSWR equation for the forward power and reflected power shown on this digital meter, 40.5 watts forward and 1.8 reflected. So we'll plug 1.8 into the two reflected power positions and 40.5 into the two forward power positions. Next, we can divide 1.8 by 40.5 and simplify the equation using the result of 0.0444444. Then we'll simplify one more step by getting the square root of 0.0444444. Now we solve 1 plus 0.2108184, and that equals 1.2108184. And we'll solve 1 minus 0.2108184, and that gives us 0.7891816. We divide the top number by the bottom one, and we've got a VSWR of 1.5341. Let's compare that with the results displayed on the Applied Engineering Science digital reflectometer. It says 1.54. With rounding, we're only off by 0.001. I suspect that slight difference is because the actual measurements sampled in the reflectometer are more precise than those displayed. Now we know how to convert forward and reflected power into VSWR. Next time, we'll take a first look at using a Smith chart. I would encourage you to download and print out the Smith chart at the link displayed here so that you can follow along at home.